Thanks a lot for inviting me for this very nice symposium. Well, I'm a trapdyne guy, so it's not I'm not, I guess, fitting into 2D materials, but let's see. I'd like to introduce the trapdyne film and see, what we can do in terms of actually really making quantum computer out of the trapdyne system. All right, so this is outline. Introduction is, well, everyone may be familiar or may not familiar with quantum computing, what quantum computing is. So I'll talk about bit, and then I'll just introduce because you might not familiar with the triptych system. So I'll talk about that. And to make quantum computer, what we need, well, we need many qubits, and we need to perform a quantum gates in good fidelities, right? So I'll talk about theory of bit, and then we'll introduce the experiment in our lab. I'll wrap up my talk. All right, so well, you probably already heard many articles about the comparing with classical quantum computer, and sorry to repeat that again, but just bear with me and just go through. Right, so the current computer is we have many different inputs, but we cannot the CPU cannot process at the simultaneously, so it has to be the compute the things with the series computation, meaning you have to repeat the process and over and over. So that's the class computer. But the quantum computer, we can use the quantum property, which is the quantum superposition state. So you can make all possible input state at once. So that if you have a many qubits, you can have basically linear sum of all possible states as an input states of your calculation. And for the quantum process is basically you have you understand your Hamiltonian, you engineer them in a way that you can perform specific algorithm, right? And then we can compute at once. So there could be massive parallel computation might be possible. Right. So while it's hard to compare the really what the counterpart of quantum computer. Well, this is some example that I found that maybe it's really close to really understanding what quantum computing is. Well, let's say we think of a little pond here, and then we drop the two pebbles here, and then the wave will propagate through time and space, and we got some results out, right? We're gonna see, well, okay, we're gonna have a pretty high probability at the center of your screen here. But let's say if you locate a rectangle or triangle boxes in somewhere in time and space, those interference pattern of wave will change, and we got some different location as answer, right? So then the question is, what kind of practical, like the algorithm will be out there by putting those boxes in time and space correctly, right? So that's what we like to do. So we basically how we locate those boxes in different time and space that basically correspond to our quantum logic circuits. So while it's a very tricky and difficult task to do so because the quantum states are very fragile, so we have to make sure that we are really decoupling those quantum systems away from environment. So somehow, let's say you prepare really those quantum system well, and you have to let it go process. So you have to interfere very well with each other and perform specific algorithm, get the results out by measurement, and you repeat that measurement process and over and over. That's what we have to do. So then basically but then the quantum computer is good at everything. I don't think so. There might be some specific task might be good for a quantum computer. So there's a few algorithms out there, which is Dokes-Josa and Shor, and then group search algorithms, and it's been known that the Shor's algorithm is basically can factor the prime number much faster than classical computer, meaning that it usually factoring number in classical computer takes exponential the time scale. We call non-polynomial, not NP problems, but if we use Shor's algorithm using quantum Fourier transform, then we can do logarithm on the top of exponential, so we can bring it down to linear. So that technically, if we have more than thousands of error-corrected logical qubit, then we might be able to solve those factoring number in hundreds of hours, which will take about 1 million years using a classical computer. But I want to make sure that, well, do we have 1,000 error-corrected logical qubit? No, not yet. We are working on it, right? So it may take some time. All right, so how that works, well, I mean, the universal logic, you have to have some universal logic gate. You cannot have infinite number of logic gate to perform the gate. So in collage computation, it should be known that the XOR or NAND gate, if we have one of that, you can create all those gates. So we call NAND gate is good. The NAND gate is a universal logic gate, and quantum computer exactly has the same counterpart, which is a single qubit gate, which is how to make a quantum superposition states. And if we can do a quantum entanglement, which is we call two qubit gates, then technically we can create any logic gate, meaning we can do any algorithms, quantum algorithms that's been proven by mathematics. So what we like to do is we like to do these two tasks with a very high fidelity and with a scaling up number of qubits. That's what we like to do. Okay, so quantum computer again, it speed up solving specific tasks, not everything, right? Not everything, only specific tasks. And maybe it's very good for optimizing multivariable problems because we can input the states with all possible states at once. So there are three advantages like this here, and then there's the quantum the circuits are well known using superconducting circuits and photons and ion traps is out there, and I'll talk about the ion trap today. All right, so condensed matter system, we have a well-known superconducting circuit and quantum dot and NV in diamond. And atomic molecular optics, we have a trapped ion, neutral atoms, and photonic system here. And there are very clear pros and cons in system-wise. So first off, the condensed matter system, well, we have many atoms nearby, right? So the quantum coherence is rather short. It's shorter than millisecond. And then another thing is you basically all the qubits are printed in a circuit board, meaning that all those the qubits are coupled through the wires, meaning that you have, if you want to communicate one qubit to another, you have to swap those qubit informations, and unless you have really high fidelity gates, it's hard to control their interactions because fidelity will drop because you keep multiplying those swap gates. But the nice thing is, well, this is a solid state circuit, meaning once you make a circuit which works, then will stay there forever. So, and then also there's a tremendous development of making the semiconducting circuits, and there's a lot of industry out there, meaning that making qubits, keep making thousands, maybe millions, might be possible, although that's working properly, that's different question. But anyhow, still you can't make qubits, right? But the atomic molecular optics field, this is individual atoms are fluorescing the light, and because it's trapped in ultra vacuum, so there's not many atoms nearby, so coherence time is pretty good. You trap atom, well, if you optimize the thing, you can get easily more than second a wave function can remain. That's nice. And you can shine the laser like a Star Wars. You can shoot the laser in any chain of atoms, and so you can do interaction quite easily. But while trapping many atoms are a very difficult task. It's a very difficult task. There are so many stable lasers and stable setup required. It's quite difficult to do so. Although people talk about maybe you can bring cryogenic systems so they can bring the pressure down further so that the background gas collision will be less, so that maybe you can trap maybe hundreds of thousands of crystal very reliably. That's what people are working on, and also I'm trying to do as well. Okay, so I'll talk about ion trap system. So let me introduce the ion trap system here. So we need the ultra vacuum chamber. We bake for weeks and weeks. So we bring the pressure down to below the reading of gauge. And then we use ytterbium as our atomic species, and it's a neutral. And you basically shine the light to where we want to trap. And then we have a neutral atom. You heat up the oven, so it will thermally evaporate. And then the one laser that have two electrons in ytterbium that kick the one electron from s to p orbital, and another light that can kick p to the continuum level, so we can make ion that way. So this distance from oven to trapping zone is less than centimeter, and then as soon as electron sees a light, it does do so for us. That's quite amazing. The time is less than microsecond. It happens within microsecond. It's really amazing. And then it's ionized, but it will move around the space and time. So what we like to do, we like to cool, and we use a well-known technical Doppler cooling. Well, the way to think is you just shooting the light to shooting the machine gun to the atom to slow down, right? In machine gun, you can think as a light. So that's how we cool down. So we can keep track the ions one by one. So this is a 5 qubit. Yes.
It's the same lasers, so there's all different lasers needed.
So all different lasers. We have two lasers, 399, 369. So 399 is starting from here to here. And then 369, well, any laser short wavelength at 370 can keep the knockoff from.
Two lasers.
Yeah, for now, two laser, right? We need two more, but so the total four laser. But actually, this ytterbium is the best in terms of number of lasers. Others are required 5, 6, 7, but we only need a 3 for qubit, 1 for qubit control. So it's not too bad. It's quite efficient in terms of buying lasers. Yes. All right. So and then I didn't talk about the trapping structure here, the device. So actually, matter of fact, that these are 4 rods out there. It's appear like this. We apply very strong AC, DC voltage. So then AC is alternating voltage basically. So the potential is high, low, zero, and low back and forth. So you can think as a take a snapshot, then you see have a saddle points. And if you let the video goes, then it will rotate the function of time effectively so that you have, if you think about the saddle points, you drop the pebble, it will drop to the low potential. But if you rotate very fast, you can effectively trap at the center. That's how we do in the ion trap system. So the charged particle can be trapped at the center. So that's how we trap it. And then, well, here, the vertical and upside up and down, the ion chain can leak out. The charges can leak out by Coulomb repulsion. So what we do here is we have n cap voltage here the side by side to avoid the ions escaping out of this horizontal directions. Yes, please. It's about 5 micron, 5 to 10 micron. So we apply like tens of voltage to apply very weak potential. That's why it's a linear chain. So this direction is very strong, so it's squeezed in this direction. And this direction is pretty weak, so it's a linear chain structure. It's formed like this way. So the species we use is so we can use any atom has a 2 electron in s orbital, right? So those are beryllium, magnesium, calcium, and strontium, barium, and there's some weirder atoms, cadmium, mercury, and we use ytterbium because as the Philip asked questions about the laser. Ytterbium is very efficient in terms of number of lasers. That's what we do. All right, so ytterbium is the same as hydrogen. I have a 1 nuclear spin and 1 electron in s orbital. So it's exactly the same as hydrogen. So physics is very easy. Not very. It's a simpler than other species, and it's pretty good to handle. So this is a trap, the vacuum chamber that my student designed. And then if you look at here, this is a trapping device. As I said, here there's 4 rods. There's n-cap voltage, n-cap electrodes to avoid the atoms leaking side by side. And again, here is an oven. Here is the oven here. So those are just the surgical tube needle, and we cut off and then put the ytterbium rod in it and then wrap it and apply the voltage and current to heat up. So this is again all made in home built. We built it ourselves basically. And then zoom in is right here. Again, there's 4 rods, there's n-cap voltages, and then if you look at the center, so this is a real time a image that we took the video of the trapping atoms. There's 1 pop up, 2, 3, 4, etc. So it's basically very strong harmonic potential well, and there are Coulomb repulsion is going on, right? So it's a perfect linear Coulomb crystal can be trapped in a way. And this is 12 qubits, and we've been recently doing 40 qubits here. And you see there's some empty zone, which that's a different isotope. So that there's a charged atom is out there, but it's just different isotope. Frequency is different, so it doesn't emit the light. But well, still we can use this one as a quantum computing as well. That's no problem.
As equation can be controlled with a 2 electron.
That's correct. And also shuttling. You can move atoms back and forth changing the voltage difference between 2 electrodes. We can move atoms around. Yes. All right. So then what we like to do, so what we have to do to make quantum computer out of this system, first thing, we have to turn many ions, yes. And then we have to do single qubit and 2 qubit gates. with very high fidelities, right? And also you have to good at initialization, detection, and quantum gates and everything. To do so, we have to do a multi-frequency phase amplitude control. We use usually the AWG, arbitrary waveform generator. So how that works is we have conventional computer has a TTL control, and that connected to RF generator, which is coupulated through the optical modulator. So if we turn on the TTL switch, then light goes to atom, and another two, then light goes to atom, and that's how we can control it. So then how well, I'm doing too much basic physics here. I mean, the how we manipulate the quantum gates here, basically dipole interaction. We apply very strong electric field to the dipole of atom, then it will couple, right? So that's dipole interaction. So that if you measure population, measure shining the laser, then you can see, or you can measure as a function of the population. We measure ahead, and we can basically pick the time. All right, this is the time for position. Then we record the time and apply the gates at that specific time. That's what we do. For 2 cubic gates, it's a little bit complicated, so I will just go through very fast. It's we using quantum motions in the ion trap system. For example, well, let's say if you want to entangle number 2, number 4, what we do is, let's say, as I said, we can not only control qubit, we can control quantum motions as well. So first, we apply laser to the number 2 atom with the carrier transition, which means flip the qubit, but we add another motion of quantum energy using those modulators, right? So then we can drive these transitions. We measure the time, and second time, what we're gonna do is we do exactly half of the time, meaning we're gonna have a position of these 2 states, right? And then what we're gonna do is the next step is we apply a second laser to ion number 4 with the flipping qubit with the removing one motion of quanta. We can again we can do that by applying the laser with the modulator with that much frequency out. So by doing so, this one will flip and will lose motion of quanta. This one will flip and will lose motion of quanta. But however, this state is impossible, right? The quantum harmonic oscillator shouldn't have a minus sign, so we'll stick as is. So then you see initial states that go to entangled state. So use the quantum motion to the entangled entrapped ion system. That's how we do. All right. So this is our lab picture about 3.5 years ago. We had a 0.7 trap, not even one, because of no funding. But I worked really hard to build system, and now we have a fully equipped 2 system, and I'm building solo one right here. Right. And then this one. So basically, our qubit frequency is 12.6 gigahertz. So you can use a microwave to drive it directly. But the problem is the microwave wavelength is too long. It's about a centimeter. But as the Chergi asked questions that ion separation only 5 micron. So you think about we are atoms and the wave of building is moving around. So we can rotate together, but not individually. So you need to have like shorter wavelengths, meaning you have a higher energy, right? So we do is a 2-photon Raman process using laser to individually address them. With using pulse laser, just details, I'll just skip it. Right? So we can do it. So this is a state detection that we have this is if we are in 0 stage, that's off resonance, so there's no light. But if it's here, then it's resonant to the upper pin level, so it can emit a lot of photons. So that's how we detect it. So basically, here is a 0 state. This is a 1 state. That's just one stage. So we basically record the histogram using PMT, and then you do if you apply microwave gate, you see Rabi oscillation that probably no decay within measurement time window. And then again, qubits are the same. So if we apply just microwave pulse, all the qubits rotate the same rate. So we see 3 qubit Rabi oscillation. With Ramsey measurement, well, half a second T to star. Even if we didn't do anything, we just trap and do microwave pulse. That's very nice. And then, but this is a microwave. We have to do individual control, meaning we should use a light. So we do that. This is the setup, very sophisticated, complicated. We need a lot of feed-forward, feedback circuit to do so, but our system is awesome to do it. But anyway, so we have a finally laser signal. So carrier transition meaning qubit flip, blue side meaning qubit plus the motional quanta, and red side meaning qubit minus motional quanta. So we do spectroscopy here, and you can see the ratio of these two red and blue sideband peak that correspond to your Boltzmann distribution of phonon. So you got phonon number about 10. And further, you can do sideband cooling. You're just pumping and you keep addressing the Rabi rate with the blue sideband. You can keep remove motional quanta. You see finally it's gone because we are all motional ground state. So we can also sideband cooling for individual atoms or motions as well. So by doing so, we can perform quantum entanglement here. So this is a quantum motional frequency of two ions, and there's a motional frequencies out there. We are using quantum motion as well, as I said before, the how to quantum entanglement. So this is we scan the laser frequency. It's a Moorman-Sorensen gate we call. This is applying red and blue sides at the same time. Before was one and the other, but now we can apply same time, then we can do better quantum gates in theory. So if I look at here, this is this is more zoomed in time scan, and you see this is a 0, 0 plus 1, 1. You see the 0, 1, 1 states almost nothing. It's very nice. But this one is not enough. While population doesn't tell you much, we have to make sure we have to measure correlation between quantum states. So we do parity measurement, see their correlations. And a month ago, students achieved 97% 2-qubit gates, so which is, I think, is pretty nice. I don't think there's not many groups can do 97%. I think even global wise. All right. Anyways, so now what we want to do here is we want to make sure this is a fidelity. But again, we are using quantum motion, so it's very sensitive to quantum motion frequencies and frequency stability. We want to make sure that we are always getting good quantum gates. The way to do it without everything is one, when we use laser pulse shaping, meaning we control laser as a function of time and space, so we all control the quantum motions precisely. And this is a preliminary data. We intentionally pick very bad fidelity, and we see enhance about 20% by shaping the laser. And this is a laser solution. So laser power is positive, negative, positive, negative, positive. So it's like a range type of 2-qubit gates. So then you can do fidelity enhance about 20%. And minus laser power meaning your phase flip by 180 degrees. So we can flip the phase of sine wave 180 degrees by applying RF with the phase off, then we can then make minus sign.
How do this is optimal phase shape go?
We measure, we can measure through the scope directly.
You
the way
basically kind of keep control, the kind of fine tuning to get the maximize.
That's right. Yeah, that's right. So we have a real-time monitor with the oscilloscope as well as the data. We optimize the phase shift. Yes.
The reason that you stopped at the 97% rather than 99 or 39.
Oh, that's good question. There's many reasons, but the biggest reason is the laser frequency is not good. It's not locked well. I mean, we need a 1 megahertz line is locked, but currently we have a 10 megahertz lock because of it's too expensive to buy that lock. Or we can do ourselves, but the what should I say? The overhead is too much. I mean, student has to work on years, and we are not guaranteed that's gonna work. So
what is worldwide record? This year?
Oh no! Now worldwide record is the Sting Group in the London. They did a 99.98%, but not using laser microwave. There's a reason for it. But the world record is 99.8. Yes.
Using the ion.
Yes, ion trap. Yes, that's right. Yeah. So that's very promising. So as a summary and outlook, what we are doing right now, the two ion entanglement is not from many chain. We have two because whether the number of ion increase, the number of motions, the complex increase. So what we do is first we trap two and shine the light, right? And now we have to do individual control. So that's we are currently doing the setup here. So you see the blinking there. That's a multi-channel modulator that they control one and the other. So we want to deliver this light to the atom. That's what we're working on right now. And then another study is basically the modulation. It's sort of our scheme of our lab. So we want to control those the laser pulse or microwave pulse. This is actually data from microwave pulse, so that you see as the detuning increase, the flat top, the high fidelity goes a bit wider, and that's what we are working right now. So we are doing, we would like to do fast gate also using laser pulse shaping, and then we are building another trap for the shuttling and actually sensing experiment as well. I'm interested in magnetic sensing, which Sergey talked about, but we also have some data already with using the ion trap as a sensor, like measuring Earth's magnetic field and canceling Earth's magnetic field, and some preliminary data on that. So the future direction gonna be is like this. While people talk about the quantum charged coupled device that you make a chip very precisely reproducibly so that people can just buy and use the chip. That's what we are planning to do as well. It's like Pac-Man game, right? So you have you separate the zone, ion loading zone, the quantum gate zone, or the storage zone. You separate them and sort of shuttle around ions. So that's basically the idea, the future direction. Another direction people talk about is integrated photonic crystal. Basically, what that meaning here is you plug the fiber from outside, right? And then light deliver to the integrated photonics and light comes out. So and trap it at the overlap zone so that you can scale up system in a way like this. So you plug and play system that's also recently very actively the research is going on. Well, I'm from Iwa University, so meaning every the students has to be female. So you see, we have four very nice graduate students working really hard, and see all the data is taken by these four students. And I'm really proud of them. And I'm a collaborator, and then also from the Duke. Well, I actually worked with Chris Monroe before as a postdoctoral researcher, and Chris has been the really biggest supporter for this whole research area, research field, and also my lab setup as well. So I really deeply appreciate. And actually, in fact, I'm working with the Chris right now with the Korea-US Quantum Collaboration Funding, and this is a really can be done by his a lot of help. And we have also other collaborators with the ongoing project. Thank you very much.
Crystal, could you have any questions?
How do we think about the Burma issue and scalability?
Some issue. Well, I mean, all the data is taken at room temperature. So while some issue, let's say the rainy season coming up, right? So humidity affect the laser functionality. So we just have many what I call dehumidify in the lab, and that's okay. So we don't have to touch every day all those fiber couplings. So later on, that's okay. So that's not a problem anymore. And also laser technology is getting advanced and more. So temperature fluctuation is not a big deal. It is a big deal, but if you do well in the lab, that's not a big deal anymore. The fact that we want to bring down to cold, it's just because of, again, the scalability, as you mentioned, right? So we want to, as I said, the room temperature, we can trap like 40s, right? And then we can cool down, then easily one order of magnitude can be done. It's already been shown like about 4 or 5 years ago by Chris also. We can trap like hundreds of them easily and low temperature. So I think that's also IonQ, you may know if they are doing that approach as well. Yeah.
So what is the current status of this one-chip kind of ion trap? The idea has been around, but then
That's right.
when you close the surface, there are a lot of charge fluctuation and those kind of
That's
things.
true, yes.
But where we are?
So right now, it's about like several years ago, people talk about building chip with the semiconducting materials, but there's too many issues, I think. Still, there's people doing it, pursuing that direction, but a lot of them nowadays are working on just glass. You have a glass, and then you do gold coating on the top and try to sort of UV handleable materials, so something more I guess material having less charging issue. So I think people are going away from semiconducting materials now.
You want kind of the metal coating because you want
Exactly.
fading this or the
That's exactly the true here. I mean the here, where was it? So just right here, you see it's gold coating everywhere to avoid the charging issue. And also that's one of the issue of integrated photonics as well, because you shine the light through the photonics, then there will be charging issue. And any light leaking a little bit, that will drive the transition. So it will affect the coherence of the atom very significantly. So people are working on how we put those gold coating layers to avoid those charging issues. That's a big issue.
I don't know whether if we just kind of forced to make the connection with this quantum material, 2D material type of things. I don't know whether there is a kind of some idea using 2D material, let's say graphene.
I wanna do it. I wanna make this trapping device. This is made by my lab. It's gold coated it's a mech core or alumina and just gold coating on the top. One piece is about $2,000. But what I want to do is just alumina, if we can do alumina and then to the graphene layer and see whether surface dirty issue is gonna be gone or charging issue gonna be better. I like to do so. I'm looking around who gonna be collaborator for graphene tracking device makers. Would you interest me? I'll be glad to collaborate.
You're limited by the nearest neighbor interaction here. How much limitation is it for the algorithms
Well, the nearest neighbor interaction, that's a superconductor qubit has the issue because the gate fidelity for the far one is too low, so you usually stick with the nearest neighbor interactions. But the ion trap is, as I said, it's rely on the quantum motions. So if we utilize a common motional mode, meaning all the ion chains moving at the same time together, meaning the far one, close one has exactly same motions. So actually it's not limited by the motion. It's more likely the nearest neighbor. Actually, ion trap is a fast connectivity between any arbitrary pair of ions. So that's fine. The problem is, can you make thousands of them? Like millions of them. Each million can be moving together, right? So those are, and frequency clouding issue, which, well, every quantum architecture has the same problem, right? So that's also later part shaping will help. So those clouds we clean up, we close all those phase spaces correctly, and those are also one of the way to do it. But the ion trap biggest issue, I think, is just scalability. How to make thousands of them stably trapped in space, right? Yeah. Yes.
So you use meta layer to protect any charge accumulation and perturbations, but with due to the use of meta simultaneously with the laser, the laser can induce the plasma.
Exactly. Yes. Very true.
Is it from any issues?
It might be, but we are really avoiding any laser hit the electrodes because anyways, the light is coming from atom, right? So if we have any scattered light through the metal, then that will totally wash out our atom signal. So we try to align, this is about 100 micron gap. So students kind of work really hard to lens in right position to skim through the center. So this is a macro trap we made. So it's hundreds of micron, but look at those peak trap. That's terrible. That's like a 70 micron or 50 micron. You have to shoot the light through. So that's very challenging, and it will, as you said, plasma issue, charging issue will occur. That's why people try to avoid away from the semiconducting materials to make those chips.
User graphene, indeed.
Yes, I want to do it. I cannot find. There's so many Koreans working graphene, but why nobody? I ask many times, but they're like, not sure we can make it that big electrodes. But I like to do so. Yes, please. Yes.
Okay, I think it's the time to close this session. Okay.
All right.
Thank you for Professor Chan.
Thank you. Thank you.